are there any questions? No? All right, let me talk a little bit about formal charges. One of the reasons we want to get rid of the formal charge is because it creates a voltage or a potential. And so if I have a formal charge on atom A here and a formal charge on atom B here, what you're doing is you're putting negative charge density on atom B, taking it away from atom A. This is like a situation that's going to be unstable, because it would be similar to generating static electricity. Like if you're walking across a carpet or something and you build up negative charge on you, and there's something to discharge that to, then electrical neutrality will be maintained. So this is not, in the sense, this is electrical neutrality because we have a positive and negative and they cancel each other out. But in another sense, it's not, because of this voltage here. And this voltage is, an electron should just easily go back. And so one example would be a case where we have a positive charge on nitrogen, a negative charge on oxygen. This would be an unstable situation. And so, like static electricity, we could easily discharge this. The way we could easily discharge it is just bring a pair of electrons in here. It's done. Then we don't have this voltage anymore to deal with. So the problem is this, at what cost can we form? If there's no cost associated with this, this is automatically going to happen, because it's unstable. But if there is a cost associated with it, well, what is the cost? Well, here, yeah, this should happen, no problem. But what if we had a situation like this? If we have a situation like this, where there's a positive charge here now, a negative charge here now, and a negative charge here now, you go, wow, that's unstable. That doesn't look good. We could easily reduce the formal charge. That is, get rid of all this static electricity here, electrostatic potential, by just moving the electrons down here, right? But does that happen in nitrate? This is nitrate, right? Does that happen for nitrate? Well, you say, sure, it could happen because we would just form this. And now we have zero formal charge on nitrogen, zero formal charge on this oxygen, and only one negative formal charge here. But is that okay? Well, yeah, we want to get rid of the formal charge, but at what cost in this case? At what cost? Well, does this structure look good to you? What's wrong with this structure? The octet rule. The problem is with nitrogen, nitrogen's got two s and two p orbitals. How many electrons does nitrogen have here? It's got 1, 2, 3, 4, 5 electrons, right? And so, you know what? We're doing hybridization now, right? And so let's use some hybridization. What's the hybridization on nitrogen and nitrate here? This one. sp2. Right. And so we got 3 sp2 orbitals, like this, and 1 unhybridized p orbital, because we're only using 2 out of the 3 p orbitals, the hybrid here. How many electrons does nitrogen have? Nitrogen has 1, 2, 3, 4, 5. So 1, 2, 3. Where's the 4th electron go? Into the p orbital. Now this is the 2, the n equals 2, right? Now the 5th electron, where do we put it? Well, the next orbital will be a 3s here. and followed by 3p up here. And so where should we put the next electron? In the 3s or the 3p? Well, you know, we have to form two double bonds, and each double bond consists of a sigma and each double bond consists of a sigma and a pi. What are the two pi bond configurations we talked about? There's the PP pi bond, or there's the PD pi bond. And so here, you know, we can form a PP pi bond because we got a p orbital here, and so the fifth electron's got to go on this p orbital here. It would be highly unlikely to go on the d orbital because the d orbital's way up there, 3d, right? And there's no 2d orbitals, are there, for nitrogen. And so the cost of doing this is a bit too extreme because there's a big jump from n equals 2 to n equals 3 in terms of energy. And so yes, of course we want to discharge this static electricity, this voltage that we just generated here, right? We want to discharge that, but we can't because there's kind of a barrier, there's a wall preventing it. And so this is like, you know, if you're about to touch your metal doorknob and you just built up a whole bunch of static, well, you just put a plastic barrier there, and you can't discharge it. And so you just maintain that. And so here, you know, the cost is too big. And so nitrogen will never form an expanded octet, nor will any of the other group 2s, right? What's wrong with that projector? Always somebody fiddling around with this. So let's talk about the advanced topic now. Well, one thing you know is this, right? Bonding in metals. Bonding in metals I'm skipping. Because bonding in metals is traditionally covered in Chem 1B. Band theory. I'll talk about MOs pretty soon. But I'm jumping over here to the end because this is more valence bond before I talk about MO theory. So let's see. It says, some unresolved issues. Can electron charge density plots help? Yes, electron and charge density plots do help. We're approaching this as from a valence bond approach. When you do this with MO, everything kind of mixes together, and this doesn't. But you know, we're using this, so we want to understand valence bond theory as thoroughly as we can. So what are we going to do here? Well, there are some unresolved issues. Okay. One, employing expanded valence shells. When we have an expanded octet, create a quandary of where to accommodate the extra valence electrons, such as SF6 and SF4. And so SF6 and SF4, we have no problem with that. Here. Actually, I need to talk. Let me talk. Before I talk about this, let me talk about this here. And so we look at this molecule here. Just for comparison's sake. We talk about having this as the octet and just maintaining the charge. The charge is minus and the charge is plus here. And the only way to maintain this kind of distribution of charge is if we have a barrier. You know, that is, if there's a way for the electrons to discharge, right? If there's a way for the electrons, then you're going to get a little shock like that, right? And so the only way to maintain this is if we have some kind of insulating barrier. Well, the insulating barrier here is energy, the potential energy. The potential energy is going to prevent it because it's going to cost too much to discharge, right? Well, over here, we think, is there a barrier here? Well, the barrier is a lot lower in energy because if we discharge it here, that is, if we just let these electrons go into the bond here, where will those electrons go? And in this case, we said they're going to go into where? You guys remember? This is yesterday. All right, so this situation is more tenable because of the energy. So what we said here is, this is going to be what hybridization? Phosphorus? sp3 hybridized. So we got 4 sp3 orbitals here. How many electrons does phosphorus have in the structure? In the second structure? The first structure has 4 with a positive charge. This structure is a neutral, so it's got 5. 1, 2, 3, 4. And the 5th electron is going to go where? So this is 3 sp3. And so we said the 5th electron is not going to go into the 4s, which is the next higher energy orbital. It's going to go into the 3ds. Geometrically, this makes sense to go into the 3d. And not only that, a double bond requires 1 sigma and 1 pi. And so here we could double bond it. The oxygen is also sp2 hybridized. We get an electron here, so we got an sp2, sp3 sigma bond, and there's a p. This p is going to come over here and form p, not a pp pi bond, but a p d pi bond. So did we cover this yesterday? We did this? Okay. So this seems more reasonable, jumping from, well, this is n equals 3, so maybe it's okay. Whereas this kind of jump here in energy is not reasonable, and so that's what prevents the voltage from discharging here. All right, and so this is what we call an expanded octet. There's 2 reasons that we expand the octet. One is to minimize formal charge, and the other is to see other reason for expanding octet. You have it in your notes, Elise? Get to the lowest energy by maximizing bonds, right? Bonding. And so we can maximize bonds. And so here, in the sense, we're maximizing bonds because, we're going from a single bond to a double bond. But this is very tricky because, double bonds are stronger, right, than single bonds. But the tricky aspect of this is a very confusing bond because this is a composite bond. This bond is actually 2 bonds here. There's the sp3 sigma bond. In addition, there's the sp2d. No, it's not that. Just the oxygen phosphorus bond. When we compare this is a single bond. This is a double bond. Double bonds are stronger than single bonds, right? In fact, we could look it up on in a chart, chapter 10. I think a phosphorus-oxygen bond's there, I'm not sure. No, probably not. Okay, over here, though, it's not just a single bond. There's another bond here that's not. Like, for example, if I have a sodium ion and a chloride ion, what holds those 2 ions together? What holds those 2 ions together is a positive charge is going to be attracted to a negative charge. This positive negative attraction is called a ionic bond. And so this is an ionic bond. An ionic bond occurs whenever we have oppositely charged ions attracted to each other, right? Well, look what we have here. We have oppositely charged ions, and they're going to be attracted via ionic bonding. And so this is tricky because this one has, this is not just a single, it's a single plus an ionic bond because of the formal charges. Whereas this is just covalent bonding. This is a polar covalent bond. Well, this is a polar covalent bond plus an ionic bond. Do you see that? It's tricky because when you look at that, it just looks like one bond, but there's going to be an ionic attraction as well because anytime there's oppositely charged ions, there's going to be ionic attractions. Ionic attractions we call ionic bonds. All right, so in molecules like POCl3 and things like SF4, do you remember SF4? SF4 was the seesaw structure. Did we do that? I think so. And we did SF6, which is octahedral. This has more than, 8 electrons. This is 2, 4, 6, 8, 10. But we know that this is okay because the hybridization, what's the hybridization here? This is sp3d hybridized. sp3d has 5 orbitals. 1, 2, 3, 4, 5. That can accommodate 10 up to 10 electrons, right? Minimize that. SF6 is going to have 12 electrons. This is a highly expanded octet, but the thing about SF6 is maximize the bonding. You can get, if you get 4 fluorines, it's great, but if you can get 6 fluorines, even better to bond. This should make them more stable. And in fact, SF6 is a very stable gas, close to inert. It's highly unreactive. It's very stable. Okay, so the question comes up that are d orbitals used? Well, this is what we've been talking. D orbitals are used. This is a PD bond, right? This is PD pi bond. This is D being incorporated in the hybridization. This, SF4 is sp3d. SF6 is sp3d2, giving us 6 orbitals to accommodate the 6 single bonds. Okay, so we talk about that. Well, actually, and sulfate. For example, when you look at sulfate in the literature, sulfate's always written like this. Let's talk about sulfate briefly. Sulfate's Lewis structure is always written with 2 double bonds, this, and 2 single bonds. The reason is to minimize this formal charge. There's a formal charge on this oxygen, this oxygen. Actually, the hybrid's going to have a -1/2 on each of these. So this is sulfate. Sulfate, what's the hybridization on sulfate? Sulfur, sulfate, sp3. And so this double bond, tell me what the double bond is. The oxygen is, what is that oxygen?
sp2.
Yeah, and so we're going to have an sp2, sp3 sigma. And what is the pi bond going to be? Well, it's going to be a P on oxygen bonded to what on sulfur? A D. It's going to be PD pi. Same thing down here. We're going to have an sp2, sp3 sigma and a PD pi. What's the geometry of sulfate? Tetrahedral. What are the bond angles? The OSO angle is 109 degrees. And so what we need two PD pi bonds oriented at a 109 degree angle. What's the normal angle of d orbitals? 90, right? And so what do you think about having two PD pi bonds? It's going to be strained, don't you think? Because the angles are off. But anyway, this is the typical structure that's written for this. But you know, for sulfate, we could have series 1, series 2, and series 3, right? For sulfate. This is what I've been doing. You know, because having two PD pi bonds at this, you know, even though the formal charges are kind of nice, what do you think about having two PD pi bonds at a 109 angle? Maybe not the best, right? And so this is why I asked you guys to write, like series 1 for sulfate structure would be just with the octet. Negative, 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 and negative. That means sulfur is +2. That's, you know, that's, when you see a +2, that's a pretty big charge. Like +2 or +3, you know, you're generating a high voltage there. Such like a +3 charge is very, I mean, you think about ionizing, this would be a second ionization energy. And so we have this structure. So this structure doesn't look so great because of the high charge associated with it. And so then we try to minimize that charge. So maybe we create one PD pi bond. We write one PD pi bond like this. We can lower that charge on sulfur to +1, which is better. And then how many resonance forms would we have for this? 4. Altogether 4 resonance forms. And then we get the resonance hybrid. When we look at the resonance hybrid is going to look like this. You know, we could draw the 4 resonance forms. The hybrid is going to be sulfur like this with 4 what we call localized or permanent single bonds on here. And then the double bonding electrons will be spread out. You know, the electron cloud will be spread out over all 4 bonds. So if we take these 2 electrons and spread it out over all 4, we're going to get 1 1/4 worth of bonds to each of these. And so I try to show what we call the delocalized electron density like this. And we say that this has a bond order of 1.25. It's a 1 1/4 bond. 2 lone pairs are permanently fixed. We call these localized on each oxygen. And then 2 lone pairs are delocalized over the oxygens. And so the delocalized lone pairs will just draw as dots like that. And so that means that each oxygen will have a charge of -3 shared over 4 oxygens is going to give you a -3/4 charge on each of these. Like that. And so when we look at this, right, this is saying, well, we can discharge some of that static electricity by giving some more electron density to sulfur. But there's got to be some kind of way to do that. And the way we're doing that in this case is creating a PD pi bond to get some electron density back to sulfur. Does that make sense to lower its charge? Because now the charge is just +1 on sulfur. That's series 2. But, you know, it's still not a stable situation because if you have a plus charge right next to a negative charge, then they're going to want to neutralize each other. But if there's no way that that negative charge can get to the positive charge, then we're stuck. But if there is a way, then maybe it will happen. And so what we say is maybe there is a way if it creates another PD pi bond. If it creates another PD pi bond, then we'll get two double bonds like this. I shouldn't erase this structure. This is the structure. And now the formal charge in sulfur is 0. There's all these oxygens here. And so this would be 3. How many resonance forms? You know, plus resonance forms. We could figure it out. You know, when I give something like sulfate, sometimes I get people drawing like 20 resonance forms to it. I don't know how they get so many, but they do it. Something like this, you know, when you draw the hybrid, you know, what's it going to look like? And so we compare. Let's compare the 3 hybrid structures. Well, actually, there's only one for series 1. All right. And so the 3 hybrids are going to look like this. Here's one with a +2 and negative on all of those. Here's the next hybrid structure where some of the electron density on oxygen has been given to sulfur. And so the oxygen's charge has gone down from -1 to -3/4 on each. -3/4 here, 3/4 here, -3/4 here. And the sulfur's charge has gone from +2 to +1. I'll try not to get too lazy. I'll tell you, organic chemists, they don't like to draw these lone pairs. They figure by the time you get to organic chemistry, you could just see those, you know, see the lone pairs without having to write them down. And so, I'll write them down. This is series 1. Series 2. Do you see how the charge density on oxygen has gone down as sulfurs? And then 3. In 3, you know, it looks very similar. You know, the bonds are going to be stronger. So rather than having a bond order of 1 1/4, we're going to have a bond order of 1 and. Did I write the bond order for this one? No. What is the bond order for 3?
How's that different from 2?
Well, the bond order from 2 is 1 double bond is shared over 4 positions. And so that means you have 1/4 of a double bond at each position. In 3, we have 2 double bonds shared over 4 positions. And so that means you have 1/2. And so the bond order is 1 1/2 here. The bond order here is 1 1/4 here. The bond order here is 1.
Well, how can you tell if that's between 2 and 3? It's 2 double bonds versus 4. Or is that, like,
2 double bonds versus 1.
yeah.
This one has 1 double bond. And so if you take that one, the pi bonding electrons and spread them out, then you only have 1/4 in each position.
Yeah. But I mean, when you just draw 4 dotted lines like that.
You can't.
Okay.
That's why we have to write it down
Okay.
like this. I try to draw more dots here, maybe, but there's no consistent method for doing that. What has the formal charge gone to? Well, the formal charge has gone from -1 on 2 of these to -2 on 4. -2 on 4 gives us -1/2. So this is -1/2. This is -1/2. This is -1/2. Right? Now we're trying to apply valence bond to something that's supposed to be quantum mechanics, right? We want the full quantum mechanical version of this. And the quantum mechanics, you can do the calculation to minimize the energy. You have these things, right? Competing things, and you just try to minimize the energy to get the most stable structure of this. And so when we're doing this, what is it? Is it going to be closer? Is it going to be structure 1, structure 2, or structure 3? In other words, take a look at what's happening. You know, we have two extremes here. The two extremes are octet, high formal charges, or minimize formal charge, expand octet. And so looking at these two extremes, is it going to be this extreme or that extreme? Did I mention? A lot of instructors, they just say, let's always do the left extreme, or let's always do the right extreme, and then just keep everything consistent. But in this case, where do you think the reality lies? Is it in the middle? Well, the reality is when you do the quantum mechanical calculations, it's going to try to minimize it, you know, and so it's going to try to give as much electron density to sulfur at a minimum cost, right? And that's going to be the best structure. And so this is why I say probably the reality is a hybrid of hybrids, you know, something in between. You know, somewhere where, in quantum mechanics, what you do is you can calculate the charge on this and see, you know, where it's closer to. You can easily calculate the charge on oxygen and easily calculate the charge on sulfur. And then kind of relate it back to our valence bond theory, because the valence bond theory is something we can do on pencil and paper versus quantum mechanics, we have to use a computer to do those calculations, and those calculations, unfortunately, are still very difficult. And, okay. So, let's continue on with this. Let me skip this for right now. All right, here. So basically, the problem arises because of this sentence right here. This is on page 45. Quantum mechanical calculations have shown that the wave functions contain very little contribution from d orbitals. What does that mean? Very little contribution from d orbitals. Does that mean no contribution from d orbitals or some contribution from d orbitals? And so, versus a significant contribution from d orbitals. And so if we have something like this, you know, with two double bonds, two pd pi bonds, do we need a significant contribution from d orbitals? No, or yes. Actually, yes, because pd pi bonds, that's a huge contribution from d orbitals. Those d orbitals are supplying the conduit to discharge that static electricity, right? Versus this, is there any contribution from d orbitals here? This is just plain sp3. And so what does this mean? Very little contribution. It didn't say no contribution, and it didn't say significant contribution, so the only way we can think of very little contribution is it's going to be somewhere in here where there is some charge delocalization due to the d orbitals, but it's probably not going to be one of these. And so this is what we call, you know, a gray area. In fact, when we look at this range, this is 0% d orbital to 100% d orbital contribution in this, right? And so it's somewhere in between. And so the way to think about this is it's not, and this is probably the wrong term to use, it's not quantized. It's not 1, 2, or 3, but it's a continuum. And there's going to be some contribution of the d, and that's going to be shown in quantum mechanics, the full quantum mechanical treatment of this. So, how do we proceed? So let's take a look at SF6 well, actually, let's see if they talk about sulfate here. They talk about sulfate. How do we proceed is like this. How we proceed is we use valence bond theory to come up with this kind of extreme range, and then we figure out that the true structure is going to be somewhere in this range. And that true structure is determined from doing calculations. We do calculations like this. This is what we get from quantum mechanical calculations. And we look at the charge on these. And so here we have the octet. Here we have the minimized formal charge. Here. And so we reach the point at which minimizing formal charges by using expanded valence shells seems best. Okay, so we expand the valence shells. However, one detailed analysis of the wave function of the sulfate anion suggests that the dominant form is the simple octet structure that does not minimize the formal charge. So you read this sentence and you go, what? So on the one hand, they're saying this is the best, and then in the same sentence, they're saying this is the correct structure based on this. So what is correct? Well, what is correct is basically it's somewhere in between, right? That's what I've been saying all along. There's going to be some kind of minimization. And unfortunately, they don't, I should have brought it in. We can do some calculations. Sulfate we can do very quickly. And we can look at the charge on the atoms. And then we can look at this. This is called electrostatic potential map. You can see, how much charge there are on the oxygens here. Is it closer to -1, right, on the oxygens? Or is it closer to -1/2? Or is it somewhere between? They're just showing and so we'll talk more about it when we go into the computer lab, which we are going to do. Okay, if there's minimal D, well, that's okay for this, for something like this. But what about something like SF6 or SF4? How do we deal with that? And so I already did SF4. Let's do SF4 again. If we do SF4, the problem is the sulfur has this lone pair, like this. And so this is an octet. Now, if there's no d orbital participation, then that's all we have. We can't bond anything else. And so if we look at the electrons and the formal charge, this would be actually 1, 2, 3, 4, 5. This would be an ion, right? That would be a cation. And cations, are they stable by themselves? No, they need an anion to bond to it to maintain electrical neutrality. Now, cations can bond to anions via ionic bonds. And so if I have another fluoride out here, then I have a mix of bonding. I have the covalent bonds to these three fluorines, and then I have an ionic bond to the fluoride. And so it's a mix. And in this way, we don't need to use any d orbitals because we don't have to provide an orbital to overlap. Ionic bonds don't require orbital overlap. Ionic bond just requires ions to be adjacent to each other. In SF6, it's the same situation. In SF6, if we want to maintain the octet, we can bond a maximum of 4 fluorines to it. And it would have no lone pairs. And the sulfur would have a +2 charge. So here's my cation. And the cation would need 2 fluoride counteranions. And so this would be a composite again. I'd have a strange cation, and the anions are just regular fluorides, and I have an ionic bond. Now, what explains the structure? What explains the structure is this. How the electron density moves here would be like this. If this fluoride comes in and tries to bond to that sulfur like this, you know, it's negative, this is positive, there's going to be an attraction. It could, if there's room. Now, it could if there's room. Well, if there's d orbitals, it would. But if there are no d orbitals, then what would have to happen is that it would have to kick out a pair of electrons in order to make room for this pair of electrons. So this pair of electrons comes in, this pair of electrons gets kicked out if we cannot access d orbitals. And so what we end up with is in SF4, we end up with 4 resonance forms. And the resonance forms are going to be unusual because it just depends on who gets kicked out, which fluorine gets kicked out and becomes an ion. So here, this fluorine is, here, this fluorine is, etc. And in order to minimize the repulsions here, it's going to adopt a seesaw geometry. And so this is a seesaw geometry without any d orbital contribution here. And so for years and years, we taught about d orbitals participating in expanded octets, but more recent calculations might suggest that it's not such a simple black and white picture. You know, the extent of d orbital. And so in this particular case, this is probably not the correct structure, nor is the sp3d hybrid structure. It's probably somewhere, what? In between the two extremes, where we have 100% d orbital participation, sp3d, versus 0% sp3. Does that make sense? And so the whole point of this last section is tough because this makes you think in terms of gray rather than in terms of a clear, you know, black and white picture. But all this is because of the failings of valence bond theory. In MO, we don't care. In MO, we just do the calculation, get the minimum, figure out what the charges are, look at the electrostatic potential map. It's very simple. And so we don't have to do all this worry about how much d orbital participation there is. The MO is going to just minimize it. Does that make sense? But valence bond is what we use to do a lot of stuff, so we should try to figure out, you know, how best to use valence bond theory and minimize the error in using it. All right, let's talk about MO, because with MO, we don't, you know, you don't have to worry about section 11.8. Because in MO theory, a bond is not orbital overlap. In MO theory, what is a bond? does one describe a bond in MO theory? Should be simple. Just hopefully you have it in your notes. Wrote it down on the board 2 days ago. Well, we're going to restrict MO theory to simple diatomic molecules only. That way you don't have to memorize an overwhelming number of molecular orbitals. And so for diatomics, it's not so bad. We do A, 1s, 2s. We're going to do it like this, 2p. And B, take out an A and out an B, 1s, 2s, 2p. And then we're going to do LCAO, and generate what's called the molecular orbital energy level diagram. And so when we do the LCAO, the 1s and the 1s, will form a sigma 1s bonding orbital. The sigma 1s bonding orbital looks like this. I'll do a different color. You can kind of figure out the shapes based on the AOs, the atomic orbitals. What's stronger, a sigma or a pi? Okay. Well, let's go to the 2s next. 2s. Oops. We do the LCAO, the 2s. We're going to get the sigma 2s here. And in energy, we'll get the sigma star 2s. Oops, I forgot the sigma star 1s here. Put that in. Sigma star 1s. Sigma star 1s is this. It's like this. Electron densities now here. The sigma 2s is just a bigger version of the sigma 1s. There's going to be nodes of course. You don't have to worry much about that. Sigma star 2s is going to look like this. The next orbital is going to be the sigma 2px. Show you what that looks like. The drawings. I'm gonna move faster. When we did the 2px, we could just take the positive and positive, for us. The positive is blue, negative is red in this case. So, this is a sigma 2px here. So let's draw that here. Sigma 2px. But we're also going to generate the sigma star 2px when we try to do the positive with the negative. In the node here. Looks like that. It looks like they're repelling each other. Yeah. It goes up here. Oops, shoot. Yeah, this is okay. I'm running out of room, but dx. Try to fit it in here, like this. It's anti-bonding. Sigma 2px. And then we have the pi's. The pi's are like this, you know. We have the positive, positive, negative, negative. We're going to get this situation here. Here we're taking positive, negative, negative, positive. It's so good. That's anti-bonding. So that's bonding. This is anti-bonding. And you can generate two of those, the py and the pz. So py, pz. Actually, this I didn't give myself enough room, but here, try. Generate these orbitals. And so basically, it should look like this. Yeah. Here's the px. Here's the sigma 2px, sigma star 2px. Here's the py, pi 2py, pi star 2py. And then we have the pz. We're going to add just perpendicular. Pi 2p, pi star 2p. When we look at the energies are going to look like this. We go kind of in this order. Actually, these are the molecular orbitals here. Look. For fluorine. You don't have to code the orbitals, positive or negative, for molecular orbitals, but here they did. This is what it looks like here, except they ignore the 1s, you know, they didn't take that into consideration. Usually we just look at the valence electrons. So we start off with a sigma 2s here, followed by the sigma star 2s, followed by the sigma 2p. I'd call it 2px, but it depends on how you define the coordinate system. And then the pi 2p's here, and the pi star 2p's, and finally the sigma 2p's. There's going to be stronger interaction for the sigma than the pi. Stronger bonding interaction, that's why the energy is lower here. And so we get this type of diagram. Basically, this is it. You just memorize it. And so rather than memorizing the whole thing, we'll just look at for the valence. So if we look at the valence, then we know sigma 2s. What's the shape of sigma 2s? So it's like that. Followed by sigma star 2s. It's the shape of sigma star 2s. That. Followed by a sigma 2p. Shape of the sigma 2p is like this. Followed by the pi's. Now the pi's are going to be degenerate. They look similar. So here's a pi 2p in the plane of the board. And then there's going to be one twisted, like this. And so one lobe's going to stick out. The other lobe sticks in. So it's just 90-degree twist. And then we have the pi stars. Pi stars look like two p orbitals repelling each other. There's a node here. Node in the antibonding ones. And so this one's going to have a lobe coming out. In, lobe coming out, and in. So the pi star 2p's. I star 2p's. We don't have to use the labeling X, Y, Z because it depends on how you define it anyway. It is defined when you solve the Schrodinger equation, but we aren't going to worry about it. And then we have the sigma star. The sigma 2p has the strongest bonding interaction, much stronger than the pi's, therefore it's lower in energy, therefore the sigma star is going to be raised in energy, equal and opposite, because it's a conservation of energy issue. So it's sigma star 2p. And so do you see the symmetry here, you know, with the 2p's? It goes 1, 2, 2, 1. And then the symmetry here with the 2s. This is expected. This is what we observe when z is greater than or equal to 8. Okay, what that means, well, what is Z8? Z8 is oxygen. And so this is for oxygen, fluorine, and neon. However, something weird happens when we're dealing with nitrogen and anything lower. There's something that's weird that happens is when we go from Z less than 8. When we go Z less than 8, well, the sigma 2s looks the same, followed by the sigma star 2s. But what happens is the sigma 2p pops up in energy. And so we have a pi 2p here, a pi 2p here. But the sigma 2p was down here, and now it's way up here. The sigma 2p, followed by the pi star 2p's, and then the sigma star 2p. This is much better, bigger than what I just drew. Well, the sigma 2p was here, and then it just popped up here. Do you see that? So the first question is, what caused the sigma 2p to pop up in energy? What caused the sigma 2p? What caused it is, this is because of repulsions with the sigma 2s electrons. And so this is an issue of shielding and penetration. When we have a high Z, what is a high Z? A high Z is high nuclear charge. A high nuclear charge pulls in electrons closer. Right? And so with a high Z, what happens is, what's more penetrating, a 2s or a 2p? What is more penetrating, 2s or 2p? S. S is more penetrating. S being more penetrating with a high Z, the sigma 2s are pulled in. Sigma 2s. If you look at a sigma 2p, sigma 2p's are less penetrating. But a sigma 2p occupies the same kind of volume here. And so this would be the sigma 2p. And so what happens is high Z, sigma 2s gets pulled in more than the sigma 2p. But the problem with at low Z, penetration isn't as significant. And so lower Z's don't have the pulling power to pull in the electrons as much. And the difference isn't going to be as dramatic between a 2s and a 2p. And so what we see at low Z is the sigma 2s isn't pulled in as much. And then when we look at the sigma 2p, well, the sigma 2p isn't pulled in that much either. Actually, this I should try to draw a better scale, but maybe you get the point. What happens is they occupy the same volume. And so at high Z, the sigma 2s is smaller because it contracts more due to the higher nuclear charge. And there's room to avoid repulsions because even though they do occupy the same volume, the 2p's occupy a slightly bigger volume here. So the 2p's have a greater probability of escaping the 2s electrons repulsions. Does that make sense? Somewhat? No? Basically, at lower Z's, the orbitals are about the same size. At higher Z's, there's more difference in the size of the orbitals. More difference in the size of the orbitals means they aren't going to conflict as much. And so here they're sharing the same room. Here, there's a little escape area where, a separate room where it's not a separate room, it's all one orbital, but, there's a forbidden area for that. It's not even a forbidden area. It's just, there's more space for the 2p. Well, if there's not much space for the 2p, the 2p's come along here and there's already electrons occupying that space, they're going to be repelled. And this is what bumps it up in energy here. And so for MO theory, this is how we do MO theory. Let's do it. Now, we have to generate the molecular orbital energy level diagram and just fill those with electrons. It's as simple as that. And so let's do that right now. And so when we do that, let's apply MO theory to first period. For first period, the MO diagram looks like this. It's sigma 1s, sigma star 1s. The orbitals look like this. That's it. And so energy goes up this way. And so if we look at H2, H2 has a total of 2 electrons, valence. And so H2 is going to have this. Sigma 1s, it can occupy 2 electrons. The sigma star 1s is empty. So when we look at an H2 molecule in terms of MO theory, an H2 molecule has 2 electrons in the sigma 1s MO. That's it. And so we look at the electron cloud density, it's going to look like this. Well, this looks similar to valence bond. Let's do a quick comparison to valence bond as an aside. Valence bond is going to be a 1s, sigma bond. And when we look at the electron density, well, there's 1 electron here, there's 1 electron here. Doesn't it look similar? We look at the electron cloud, it looks similar. So maybe valence bond is not so bad, because it came out close to the quantum mechanical picture. All right, in quantum mechanics, we can get a lot of information, but we're only going to get 2 pieces of information for us. 1 is the bond order, 2 is the magnetic properties. I already wrote the equation for bond order. This is what I was asking for earlier. Hopefully you have it in your notes. The bond order is equal to number of bonding electrons minus the number of anti-bonding electrons divided by 2. right? And the bond is described in MO theory as what? Well, I'm not going to repeat. You'll look it up, because I think if I just say stuff, it doesn't click. Because the bond order is 1 here. And the magnetic properties, we look for diamagnetic or paramagnetic. Dia versus para. Well, this is going to be diamagnetic because there are no unpaired electrons. And then we look at an electron density map. This is called electron density map. An electron density map, this is crude, but this is our electron density map here. We want to know the electron densities arranged. We can get exotic species as well. So let's go H2 plus. If we do H2 plus, there's only 1 electron. And so this becomes bond order 1/2, paramagnetic. And the electron density map is we just have 1 electron here instead of 2. But this should exist because there's a bond there. If we do H2 minus, will H2 minus, can you form an H2 minus? Like give a hydrogen molecule an extra electron? Using MO theory, yeah, you can, because what would happen is H2 minus has now 3 electrons. So we fill up the MOs with 3 electrons. Sigma 1s is going to be full. Sigma star 1s is going to have 1 electron. Like that. This should exist because this has a bond order of 1/2. So it's not the strongest bond, but it's got a bond, and it's paramagnetic. And when we look at the electron cloud density, the electron cloud density is we've got to add in the antibonding orbital now. So we add in the antibonding orbital, and it's going to have 1 electron worth of density there. And so this would be an overlap or overlay of the sigma 1s and the sigma star 1s. We could look at HE, HE2. Actually, oops, stopped ahead. So let's look at HE2. HE2 is going to have 4 electrons, 2 in the bonding, 2 in the antibonding. Cancel each other out. HE2 should not exist. Whereas HE2 plus should. HE2 plus is 3 electrons. 3 electrons. And so this is going to have a bond order of 1/2. Even though both of these have a bond order of 1/2, the bond length is going to be totally different. HE2 plus is going to have a much shorter bond because Z is much higher. Should have a stronger bond, even though both of these are bond order 1/2. And so applying MO theory is easy. The hard part is memorizing the MO diagram. But if you know how the MO diagram is generated, it helps a little bit. And this is how it's generated. Well, let's just apply it. Because once we have it, then we can do it. Li2 would be an unusual molecule, but it would have 2 valence, one from lithium, the other from lithium, so 2 electrons total. And the sigma, this is 2s, 2 valence electrons. So this is the second period. This is bond order is 1. It's diamagnetic. We could look at an electron density map. We just have electron density in the sigma 2s. BE2 shouldn't exist because it's got 2 electrons in bonding, 2 electrons in antibonding. B2 should exist. B2 should have a single bond between the 2 borons. It should be paramagnetic. You have sigma 2s2, sigma 2 star 2s2, and then we fill the degenerate pies one at a time, parallel spins according to Hund's rule. The diatomic carbon, we should be able to form 2. This should have a double bond between the 2 carbons here, like this. How does that compare to, how does this compare to, well, maybe we'll look at carbon, but how does this compare to valence bond theory? Does valence bond theory predict that diatomic carbon shouldn't exist? And so let's take a look at valence bond theory in terms of diatomic carbons. actually. And so valence bond theory, what do you need first for valence bond theory? The Lewis structure. From the Lewis structure, we're going to get this. Carbon, carbon, carbon's 4 electrons, 4 electrons. So 1, 2, 8 electrons total. 3, 4, 5, 6, 7, 8. Something like this. So we'll take a pair here and bring it here. We got something like this. Right. That right, 2, 4, 6, 8. And then it doesn't quite have an octet. And so I'd like to triple bond it. Just go ahead and do a triple here. Something like that. But this creates a free radical here. It creates a free radical, but I'd rather have a free radical than maybe this, because this creates what? This creates formal charge. This would be 1, 2, 3, 4, 5, negative here, this is positive here. Is that stable? Not at all. And so we're probably stuck with something like this, unless we do something like this. Maybe we do this, the quadruple bond. Do that quadruple bond. Yeah? Could we do it in valence bond theory? No, because a triple bond's okay. Because what's the hybridization here? Actually, I didn't do a triple bond, but we won't do a triple bond right now. This is a very unusual molecule, but let's do this. You know, H2C2 acetylene is no problem, because if a hydrogen comes over here, the bond here, a hydrogen comes over here, a bond here, we'll make H2C2, right? To knock off those hydrogens, we're going to have a very unstable molecule, C2, but that's what we're looking at here. A very unstable molecule is going to be reactive. It's going to want to form more bonds, right? And so let's analyze this by this one. Even though everything has an octet, this has an octet, this has an octet, the problem is the bonding. You know, why isn't this good? Can you explain to me why that isn't good? Well, because you memorize carbon likes to form 4 bonds. Well, that's 4 bonds right there. It's just a quadruple bond. So why isn't the quadruple bond okay? Because you memorize, well, maybe because you never heard of quadruple bond. Quadruple bonds do exist. So why don't I expect a quadruple bond here?
Is it because carbon can't fill at the orbital or something like that?
Yeah, right. Because we're going to run out of orbitals, bond. When we come up with the triple bond, what's the hybridization here? SP. And so when we have a carbon and SP hybridization, we'll have an SP orbital here and an SP orbital here. And so we've used 2 of the p orbitals. No, actually, 1 of the p orbitals. That leaves 2 p orbitals left over. So here's 1 p orbital, right? Where's the other p orbital? The other p orbital is going to be perpendicular here. And so in this, you know, carbon's going to have 4 electrons. 1, 2. This is going to be a radical in this sp orbital over here. 3, and this is going to be a bond. We can bond this to the other carbon. The other carbon is going to be here. This is going to be sp, form sp sigma bond. And we can form 2 pi bonds, right? This would be a pp pi bond here in blue, and a pp pi bond in red. And then in this other sp, we'd have another free radical. And so there's no problem, but now if I'm trying to make a quadruple bond, what's the hybridization here? Well, I don't know what the hybridization here is. Maybe sp with an empty sp orbital? You know, but when we try to do the orbitals here, it just doesn't quite work out, where we can quadruple bond a carbon to a carbon. There's no d orbitals we can use on this. Well, anyway, in valence bond, I predict a carbon-carbon triple bond, paramagnetic. In MO theory, I predict a carbon-carbon double bond, diamagnetic. When I look at the electron cloud, do I have a different color for the electron cloud? Oh boy, I'm going slow. I need to speed up. I was getting too far behind. That means I wasn't planning to lecture tomorrow, but I got to lecture a little bit to finish this chapter. When I look at electron cloud density, I got the pi density here from blue, right? And then I got the sigma density here, and then I got the pi density here, chlorine from the reds, and then I got some radical density out here. And so when I look at the electron density map, it kind of looks like this, you know, where you just tap out where the orbitals overlap. But let's compare it to the electron density map that we get from MO. The electron density map that we get from MO looks like this. We got 2 electrons and a sigma 2s. And so, okay, here's a carbon, here's a carbon. So we got 2 electrons and a sigma 2s. Okay. And then we have a sigma star 2s, 2 electrons and the sigma star 2s. So the sigma star 2s is this. Actually, I should have done the electron density probably in different colors. So I got 2 electrons worth of density in the sigma star 2s. And then I have in the pi, I have electron density here. So one of the pi's I'm going to make like this in the plane. So I get electron density in the pi here. And then one of the pi's I'm going to make out of the plane. So the pi that's going to come out of the plane, I ran out of colors, so I'm going to just use a different outline for this. This is the pi coming out of the plane, and then there's the pi going into the plane. And so in some respects it does look similar because I have pi electron density here in the plane and pi electron density coming out of the plane and going into the plane, like this. Right? But this is wrong because, you know, this predicts a radical. This is not a radical. I have these electron densities in the anti-bonding, which is kind of similar to having the single electrons in the sp orbitals pointed out, right? And so in some ways it's similar, in other ways it's different, you know? But the bond order here is only 2, whereas the bond order in the valence is 3. Now which one's correct? Well, which one's correct turns out to be MO. MO's correct. All right, well, you know, C2 is not an important molecule because C2 is a free radical, right? It's not stable. N2 is an important molecule. And when we look at the electron density map in N2, it looks very similar to what we get in valence bond. And so the valence bond picture of N2 and the MO picture of N2 are similar. They both predict triple bonds. They both show pi density and sigma chi density, and they both predict diamagnetic. The major problem with valence bond comes with not N2, because N2 works nicely, not with F2, because F2 works out kind of nicely, but with O2. O2 valence bond and O2 MO are totally different. Well, not totally, because both predict a double bond. And so let's take a look at O2. Actually, maybe I'll finish. This is pretty much one of the final things I wanted to say. We still have 5 minutes, right? I think I'll finish chapter 11 right now. All right, O2, valence bond. O2 valence bond, what's oxygen's hybridization? sp2. And so that's easy. sp2, I'm going to write my 3 sp2 orbitals in the plane here. 2 lone pairs, one bonded to another oxygen, sp2 here. And then 2 lone pairs out here. And then I'm going to have my p orbitals, so, you know, this p orbital is going to stick out here. This is a p orbital, another p orbital that sticks out here. And we're going to have pp pi bond. So we got the sp2 sigma and pp pi. And then I'm going to tilt this so we can see it. This is a top view. We're going to look at it from the side view. When we look at it from the side view, then we'll look at, primarily we're looking at the pi bonding, but we'll just show the sp2 sigma bond here. Right. And then this sp2 lone pair sticking out, this sp2 lone pair sticking in, this sp2 lone pair sticking out, this sp2 lone pair sticking in, sp2, sp2. And so we've got the trigonal-planar arrangement of sp2 orbitals. And then the pp pi bond can more easily be seen here, the pp pi bonds like this. And when we look at the electron density distribution, we can kind of map it out, you know. Here, that's the density here, the density pi bonding the density up here, pi bonding density down here, lone pair density out here, lone pair density out here, here, and here. And so this gives us electron density map of the O2 molecule. And what we say about the O2 is it's diamagnetic, and the bond order is 2. It's a double bond. But when we do O2 using MO theory, O2 with MO theory comes out, well, double bond, so that's good, same as valence bond, but it's paramagnetic, not diamagnetic. And so what in O2, the electron density map is totally different than what we had here, you know, for this. And so let's take a look at the O2's density map. And this is tough because we got to write so many orbitals here for O2. We got the sigma 2s, it has 2 electrons. And so I'll try to just do it with sigma 2s. And then after the sigma 2s, we have the sigma star 2s. And then after the sigma star 2s, we have the sigma 2p. So we'll do a different color. Now, are the 2s and the 2p going to interfere with each other? In other words, is this a high Z or low Z? This is a high Z. That means the sigma 2s are being pulled in tighter than the sigma 2p, so they don't interfere with each other, right? And so the sigma 2p's being pulled not as hard as the sigma 2s. So the sigma 2s contracts and gives more breathing room to the 2p electrons so they don't bump up in energy. After the sigma 2p comes the pi 2p's. Now the pi 2p's, you know, right out here, we got one pi 2p in the plane, which is going to have 2 lobes like this, right? And then we have one pi 2p coming out of the plane. What color shall I use for that? Red. Well, the one pi 2p coming out of the plane, we got the lobe here and then the lobe going in. So this is the other pi 2p. And so this is the pi 2p in the plane, this is the pi 2p perpendicular to the plane. And then we've just filled this in with electron density, right? We fill this in with electron density and compare. You know, when I fill it in with electron density, we see that the pi 2p's only have 1 electron's worth of density over here, whereas the pi bonding electrons here have 2 electrons worth of density here. Here, and perpendicular, another 2 electrons worth of density. And so electron density is distributed differently in space, in MO theory here, than in valence bond. And so MO is accurate because oxygen is paramagnetic. You know, there's a classic demonstration. Liquid oxygen is attracted to magnetic fields. And that can be readily observed, and so it's a fact that O2 is paramagnetic, not diamagnetic, and therefore valence bond theory, unfortunately, is wrong. All right, well, I'm going to stop here and continue.